Alright, this is the second lesson in radicals, and we're going to have the product and quotient rules for square roots, or what we now call radicals. And the first one is the product property. And this is going to give us another tool to simplify radicals. We have the square root of AB. That can be rewritten as the square root of A times the square root of B. That's it. That's the product property. Where you see it is if you were given, say, 9x squared. You can mentally, or on paper if you want, break those into two separate radicals and see that the answer is 3x. You can have 81y to the fourth. Well, the square root of 81 is 9. Y to the fourth is y squared, right? And you can even make some a little bit bigger. 121 x squared, y to the fourth, z to the sixth. You should recognize the square root of 121 is 11. Square root of x squared is x. Square root of y to the fourth is y squared. And the square root of z to the sixth is z to the third. Excuse me. From there we go on to the quotient property of square roots. And product is multiply, quotient is division. All this is saying is that the quotient property says if you have the square root of a over b, you can change that into the square root of a over the square root of b. And where you see that pragmatically is in a problem like this. 9 divided by x squared is simply going to be 3 over x. The square root of x squared y squared over 16 will be xy over 4. And one more, and then we'll do some other further positioning examples. That'll be 2x squared over y. And then you see them in reverse sometimes when it comes to simplifying radicals. You'll see problems that look like this. The square root of 5 times the square root of 10. Well, neither one of those separately can be simplified. 10 is 5 times 2, 5 is prime, but neither one has a pair, so they can't be simplified in that fashion. But they can be multiplied by using the reverse of the product property. The two separate radicals multiplied together can be 1. That'll be the square root of 50. But then 50 does have a pair in it, so that can become 5 square root of 2. Works with variables as well. So if you have the square root of x cubed, x to the 7th y cubed, times the square root of x to the negative 1y. Well, remember going back to our exponent rules, when we multiply like variables, we add their exponents if they have the same base. So 7 and negative 1 make 6. 3, and we have an understood 1 there, makes 4. So that becomes x cubed y squared. And I've got 4 more examples to go over, and then we'll be done. So square root of 14 times the square root of 2. That can become the square root of 28. When you factor 28, you get a pair of 2's, so the 2 comes out, the single 7 stays behind. We can do it with multiple variables. So that means we have a total of 6 A's, 4 B's, and 2 C's, which will give us a final, when they come out, 3 pairs of A's, 2 pairs of B's, and 1 pair of C's. If you see a problem, you might see square root of x to the third times square root of x squared. That becomes the square root of x to the fifth. Well, if you have 5 x's in there, you have 2 pairs, so you have an x squared coming out and 1 x staying behind. Then I wanted to show you, actually I have 2 more examples. One interesting problem that you'll see come up a lot. We've never seen anything like this. Now we're adding things together inside the radical. But take a close look. That's a trinomial, and you may recognize, and this is how math is all tied together in a lot of ways, that that's a perfect square trinomial. It factors into a binomial squared, then the square and the square root cancel, and you're left with x minus 3. The other example I had like that is same process. That becomes x plus 8 squared, so your answer is x plus 8. Alright.